Hey Code Websters, welcome back. I've been away for a week, doing no videos since then. That was mainly because I had an exam, but back at it again. All right, so today what we're going to be doing, we're going to develop our digit analyzer like we did in our last video, but we're going to use Tensorflow instead of slogging our way at it from scratch. So Tensorflow, if you haven't heard of it, is a system that allows us to develop AI using simple packages and even simpler user interfaces. All right. Before you actually begin this tutorial, I want you to watch the video. It's going to pop up around here. This video will explain how to install TensorFlow, install PyCharm, so you can follow along really succinctly. Okay, so let's go jump right into it. I'll import several packages which you'll install using pip install. Okay, so the first package is TensorFlow. You install that. Then you got matplotlib, you got NumPy. Those are mathematical packages. Then you've got the image analysis packages. For this one, you're going to go pip install pillow, but you're going to import it using pill. And this is just CV2, so you go pip install CV2. All right, now we can just get right into the actual code. So what we need to do first is get the MNIST data that we used in our last video. But since this data is already in TensorFlow packages, we can simply import it using TensorFlow. So let's go ahead and do that. Okay, so that's the MNIST data, really simple. Next, we need to actually extract our training data and our testing data from this. Now, the training data will be used to train our system. Essentially, it brings our baby to life. The testing data is just to test our little child and see if it works properly. All right, now that we actually have our data, we need to normalize it. Normalization is basically transforming our data from being 0 to 255, because that's what we use in colors, to 0 to 1, all right? Okay, notice we're not going to actually normalize our Y data because the Y data actually just holds the information corresponding to the labels. So for instance, you'll have 1, 2, 3, 4, 5, 6, 7. All right, so we actually want that data, but the X data is just, we're just looking for the patterns in the X data. So now we actually want to create a sequential model. Essentially, a sequential model is a model that has one set of inputs and one set of outputs. There are other types of models, but we're not going to be getting into that today. Okay, so next we need to understand that our MNIST data is in a 28 by 28 array. We want to transform this into a 1 array by 784. All right, so the way to do this with TensorFlow is simply telling our model, hey, we're going to import some weird system which has x by x. We want to transform that to 1 by x times x, all right, where x is the dimensions. Okay, so the way to do that is using a function called flatten, and we're just going to implement that into our model. Okay, so that's essentially our input layer. We next want to develop our hidden layers, all right? So we'll have two hidden layers of size 500 and size 128. We'll be using the rectified linear unit activation function, which is denoted Relu. Basically, this sets every negative value as 0 and every positive value as being the same value unchanged. So let's go ahead and do that. Okay, so as you can see, we've set up two hidden layers. Finally, we actually want to do the output layer. So for the output layer, we're going to use something called Softmax. That's going to be our activation function. This is just a probability estimation function, because if you remember from our last video, our outputs are going to be a bunch of probabilities for an array of size 10. The 0th place, obviously, is a probability associated with our image being a 0. The first place is correspondingly the probability that the image is 1, and so on. All right, so we're going to be using Softmax. Okay, now before we continue, I've added some links in the description explaining the rectified linear activation function and the Softmax function if you want to get into it a bit more deeply. So next what we want to do is actually compile our model. This essentially implements the logic we'll be using to optimize our network, or more specifically to optimize our weight matrices, and what metrics we want to keep a hold on that we want to output. So we're going to be using the Adam algorithm and the sparse categorical cross-entropy loss system for our model. If you want to get a bit more information, I've added links in the description for that as well. And obviously we want the matrix accuracy. Finally, we actually want to fit the actual model. So everything up till here was just the generic model. Next, we want to actually use our data and fit it and check if this model is working pretty well. So let's go ahead and Okay, so now that our baby is alive, we want to test it, right? So some parental guidance. Let's see if it's working pretty well. So we're going to evaluate this. Okay, so that's actually going to give us our loss, which is using that, and it's going to give us our accuracy, so the accuracy and the loss. All right, so we just want to print those out to see if it works. All right, now I'm just going to go ahead and run this. All right, so our system shows a loss of about 0.083, which is really good, an accuracy rate of 98%. So for this testing data, this is really good. Obviously, there's some overfitting because we're using MNIST data to actually test it. But yeah, it's a really good system. So let's go ahead and actually use our own images like we did in the last video and see if this works to adequately analyze our own images. So just as in our last video, I'm going to import a function, right? If you want to learn a bit more about this function, you should watch my last video. I've also added the function in the description, so you can just copy and paste it as well. Generally, this function basically allows images to be placed into our neural network, right? So it's just a bunch of image analysis technique. Okay, now that we've got that function, we want to actually next develop a simple loop. This loop I'll explain the loop afterwards after I write it down. Okay, so let's go through this loop in a bit more detail. So while true means, hey, let's go through it forever. Enter the directory. So I've got a bunch of paint images here. I'll show you how you can make those next. Print the corresponding value. So you input a value which corresponds to the image. So that's the real value. You get the image data. You prepare the image from the directory. You then let the model actually predict what number it is. You get the label from the prediction, right? You get the highest probability, and that's the prediction. And then you say the network says label, and then its corresponding probability. Then you get the real value and compare it. If it's the same, match, otherwise no match. So let's go ahead and run it. All right, guys, everything's loaded up. So let's go ahead and go to Paint. I'm using Paint. Then what you can do is you can press resize, go to pixels, change that 28 by 28. You don't have to get rid of this, so you can actually change them differently. Then you can just put a number in there. That's what I did. You can put 7 or whatever number you want. I already have that, so I'm not going to bother doing that. Let's go ahead and try 6 first. So this is how you enter directory. Remember, you need a dot at the front, then 6.png. And then I'll say, hey, that's a 6. What does your computer say? So the computer says, hey, that's 6 at a probability of 95%, 96% pretty much, which was really, really good. Let's go ahead and try something else. 7.png. 7, right, it says 7, and that's got a probability of 100%. Let's go 9. Now, I've intentionally drawn the 9 a bit weird. In the MNIST data, it's a bit different. So let's go ahead and check that. I have a feeling this will give me 1 maybe, or 8, because it kind of looks like an 8. If you look, there's one big circle, so it would give an 8 at a high probability. So we'll go 9. Yeah, so it says it's 8 at a 99% probability. As you can see, this isn't that good at identifying numbers, and that's because we're using different data. All right, so if you wanted a more succinct data, you would use your own handwriting and store a bunch of data and compare that. Let's try 3. Don't think we've tried that. .png. So if you want to see the images here, that should give me a 3, shouldn't it? Yeah, it's a 3 at 96%. Then you got 4, which is a good 4. That's not a bad 4. I'm pretty sure I think this our little baby can Yeah, it's 4 at 100%. Now, 5s are really bad at analyzing images. I don't know why. It's something I've been working on, but I know convolution networks work better. And that's what we're going to do next time. We're going to actually develop a more intricate system which works specifically for images. Yeah, so it says it's a 9, which I guess doesn't look like a 9 to me. But the computer actually sees differently, right? So it might see some patterns normally with a 9 and then say, hey, that looks more like a 9. But yeah, guys, anyway, this is everything. Hope you've enjoyed this video. Like and subscribe.